In this video, I'm going to talk another types of models for applications of first order differential equation, all right, which is Newton law of cooling, all right, Newton laws of cooling, all right. We mainly talk about the coolings, all right. Newton's law of cooling. So we usually talk about the coolings, means that definitions at which that Newton said that the rate of change of the temperature, all right, the temperature of an object, all right, is always directly proportional to the difference between the temperature of that object at that time to the surrounding temperature, all right. We said the surrounding temperature. So where theta s is a constant, as surrounding temperature will not change, all right, because the object and a very bigger room, right? For example, aircon room. So the temperature of the surrounding temperature is constant, right? So which is the object will be, let's say a heated object, the temperature will be reduced until minimum will reach the surrounding temperature according to Newton's, all right? Or we said the first thermodynamics law, right? The thermal equilibrium, right? An object, let's say a heated object, you bring it to a room temperature, right? So if you from time to time, after for very long period of time, so the temperature of the object at the lowest point, the lowest temperature will be the temperature of the surrounding temperature as they would reach a thermal equilibrium according to first law of thermodynamics. So as this is okay, that is the law, and let's look at this. What is the meaning of this, right? So the rate of change of temperature is directly proportional to the difference between the temperature and the surrounding temperature. The meaning what? As the temperature here is higher compared to the surrounding temperature, the rate of change of the temperature will be getting very higher, right? Or we said the rate of release of heat is higher. For example, you touch a for example, I have an object in 200 degrees Celsius. With the surrounding temperature, room temperature is let's say 23 degrees Celsius. All right, there is a huge difference, right? A big difference. So 100 degrees Celsius and a 50 degrees Celsius and an object that 30 degrees Celsius. Which one will be more painful when you touch, right? Based on logic, right? You will know that you will touch this, you will feel, wow, very pain, right? Maybe you have injured, right? The heat injured. So this one you will feel like, wow, very hot. But this one is, you can touch, right? You can feel, you can still play around with this, okay? And this one you can just put your hand inside, okay? Just take it over. Because why? The heat transfer become lower, right? So as the heat become, this one, as you just touch, you feel the pain. Why? Because the heat transfer from this object to your hand is very fast. Because why? Because the difference between this temperature and the surrounding temperature, the difference is very big difference, right? Very big difference. This shows this is true, right? Because the bigger the difference, the bigger the rate of release, of heat. So as it's getting nearer, so this one also will be reduced. They are directly proportional, berkadar secara langsung. Meningkat, dia meningkat. Menurun, dia pun menurun. Itu maksudnya directly proportional. As this is a decreasing rate, right? It's a decreasing rate. Means that we usually, it's okay to put just a K here, right? It's the same thing here, right? You just put a K, it's okay, all right? But you must know that the K is actually a constant which is less than 0, right? Or if you put a negative K, of course K will become positive, right? K will become positive. This is not a problem. If you put negative K or you put a K, it's okay. Why I say that you can put a negative K here, because this is a decreasing, means that the temperature of the object is keep decreasing, right? So it's a negative rate, all right, negative rate. So it means that it's a negative rate. So, all right, so I just put negative K just to tell you that it's a negative rate. But it's okay to put a positive K. But you must understand the value of K will be a negative value when you put a positive there. So now, okay, this will be the definition for Newton's law of cooling. So as I convert it to become an equation from the relation, so and I can solve this one by using the knowledge. This is a physical knowledge, right? Physics knowledge. So for this, it's become a mathematical knowledge, which you need to apply the first order differential equation. So as d theta, right? I just do separation of variable, okay? And I make the dt over there as I separate the temperature one side and the time one side, then I integrate both sides, right? So let's see how I derive the formula for Newton's law of cooling for the temperature. All right, okay. So as this is a constant, right? This is just like integrating 1 over x minus 1 with respect to x. If you see carefully, or dy, right? Dy y minus a constant, right? A constant. So this is a constant. So if I integrate this, I will getting ln y minus 1, right? So I just putting ln theta minus theta s, as I no need to put a modulus here. Do you know why? Because theta was always exceed, is always minimum. So means that it will exceed, definitely. Somehow they will exceed the surrounding temperature, right? Because this object won't lower than the surrounding temperature. So then we try to derive this one, and if we integrate this one, I will getting negative kt. Remember, this is a constant. This is constant. Suppose you need to bring out the negative k and you integrate 1 dt, right? Integrate 1, you're getting negative kt plus with c, right? So now we try to, as this is a log e, as ln theta minus theta s is log theta minus theta s to the base e, right? So as you can bring over there, it becomes theta minus theta s equals to exponent negative kt plus c, right? Log base e. So we bring over, become exponent negative kt plus c. So as I in the previous lesson for application, every models, when you look at this, you can rewrite this into negative kt multiply with ec, right? Because if you multiply, it's shown its addition. So, alright. So now I'm going to rewrite this as a, as this is also a constant. It's a constant. So it becomes a e negative kt. And finally, the formula for theta in terms of time. It depends on the time. It's negative kt plus with the surrounding temperature. So this is the model. This is the models of Newton cooling, and this is the formula for finding the temperature of the object after time t, right? So I hope you understand this derivation before you solve a problem related to Newton law of cooling. So, all right, let's look at examples. All right, okay, let's continue with this example. Okay, you can read the question first. When a metal is removed from an oven, of course, you put it in an oven is because they want to heat the metal, right? So its temperature is measured at 300 degree Fahrenheit and placed at room temperature of 70 degree Fahrenheit. So means there is a difference between the temperature of the object and the temperature of the room, right? So there is a change of heat, exchange of heat. So 3 minutes later, the metal is 200 degree Fahrenheit. All right. Of course, the temperature will be dropped as the temperature of the surrounding is lower. So find how long it takes for the metal to cool to 150 degree Fahrenheit. This is the case of Newton's law of cooling. As a metals that are heated, is bring to a room temperature which is lower compared to the temperature of the object, right? So as you must understand that the room temperature will be constant, right? It will be constant. So then according to this information here, we have know that the initial temperature, right? Suhu awal. So usually we will define some variable for these cases here. So when the time initially, the T is 0, the initial condition, the temperature of the object is 300 degree Fahrenheit. Right? After some time, means after 3 minutes, from 0 to 3 minutes, according to here, 3 minutes later, the matter temperature is reaching 200 degree Fahrenheit. Right? So, and the question here is take how long for the temperature to reach 150 degree Fahrenheit? Right? So we have to use the data, right? The given information here to get a formula, right? As this matter, different matter have different rate of cooling, right? So now we are studying about this matter, right? Maybe we don't know what is this matter. So according to scientists, there is a table. So as we calculate the rate, we can know that what is actually this matter, right? It can be any type of matter. So so now, as you know that the derivation just now, as I derived that d theta dt is directly proportional to the difference of temperature of the object and the surrounding temperature. As I derive, when you're solving this problem, you have to derive everything. Yes, you have to derive just like what I do just now. All right, you have to derive everything and have to tell what is happening, right? So after you derive, you're getting a formula, right? You can play back the video. So you were getting a formula where there is a AE negative KT plus with surrounding temperature, right? The surrounding temperature. So according to Newton's law of cooling, this is the formula, right? This is the formula. So our target here is to find the value of A and the value of K, right? For every problem here, we have to find the value of A and the value of K. So we use the condition here. So when T is 0, so we substitute. When T is 0, the temperature is 300 degree Fahrenheit. So we substitute 300 into the equation. So AE negative K T multiplied with 0 as when the time 0 plus with the theta S. What is theta S? This is a surrounding temperature which is already given. Where is it? The room temperature is 70 degree Fahrenheit. So this is the first thing that you should do. So to find the value of A, and this will be 1, e power of 0 is 1. So A will be 300 minus with 70, which gives you 230, right? So you have A to be 230. And of course, secondly, you have to find the value of the cooling constant, right? The cooling constant. So now we substitute as we improve the formula have improved to become theta equals to A, which is 230 E negative KT plus with 70, right? 70. So you want to find the value of K. So we're using the second information, right? So theta is 200. 200, right? 200. When the time T is, so your A is 230. A is 230. E negative K multiplied with 3 plus with 70, right? So now our target is to finding the K. So solving this equation, 200 minus with 70, we have 130, right? Minus 70, we have 130. So 130 equates to 230 exponent negative 3K. And simplify this, we have 13 over 23, right? 13 over with 23, which is exponent negative 3K, right? Exponent negative 3K. So as usual, you know that you have expert in this, so you're putting ln both sides. Solving as you're putting ln both sides, ln exponent 3k, right? Ln exponent 3k. So as after you're putting ln, you know that this you can bring forward here, right? You can bring forward here. So you were getting ln 13 over 23 equates to negative 3k, right? Equates to negative 3k as ln e have already become 1. So the k will be negative 1 over 3, right? 1 over negative 3 ln 13 over 23. So this is the cooling constant here, right? The constant means that this K is specific for this metal only. Maybe this is aluminium. Maybe after you finding this, a scientist can refer to a certain type, just like periodic table. They refer to a table. They can refer. Oh, this is actually an aluminium metal, right? According to this constant here. So this is very important, right? As you study first order differential equation. So, but after you know the K, so you have improved the formula, become a complete formula for this metal. Alright, the cooling formula for this metal. So which is 230 exponent negative, right? Negative K. So, and this is negative. So negative, negative, positive. So become 1 over 3 ln 13 over 23 T plus with 70. Finally, you have got the formula by using the knowledge of differential equation, which is you using the method of separable of variable, right? So now I'm going to solve. I have getting the formula. I can solve the problem now because the question asks find how long it takes for the metals to cool to 150 degree Fahrenheit. So you just replace the theta with 150 degree Fahrenheit and you rearrange. You can find the value of T. All right. Let's see what's the value. All right. Okay. So you can replace with theta is 150, just like you are doing some science question, right? Or you can do some experiment during your labs, all right? I think every student that studies science know how to do this. So 23 multiplied with T plus with 70. So this is a mathematician doing to getting this formula. And a scientist is just using this formula to getting the values, right? So, and 150 minus with 70, right? 150 minus with 70, 150 minus with 70 divided by 230. So we have 8 over 23. Everything I was using the exact value without convert this to decimal. But it's okay to convert this to decimal. But you must give a more decimal value, right? Decimal places so that you can getting a correct. But this is even accurate, right? So if you not convert, so you're getting 8 over 23, everything 8 over 23, 8 over 23 equals to exponent 1 over 3 ln 13 over 23 time, right? Time. So then you have to need to put the value of ln both sides. So that what you can do. So as you put ln here, you know that as you put ln exponent 1 over 3 ln 13 over 23 time, you can bring everything here over here, right? As the ln e will become 1, right? Ln e is become 1. So you have ln 8 over 23 equates to 1 over 3 ln 13 over 23 multiply with times. So of course you're taking this everything here, divide by this number here. Okay, let's see what you will get, right? So let's calculate. Alright, so which will give you around, alright, after you round off, is around 5.55 minutes, right? 5.55 minutes. So means it takes 5.55 minutes for the object to cool from 300 degree Fahrenheit to 150 degree Fahrenheit. So this formula is very useful. Let's say this is a formula you can apply for this method, right? And this formula you can use to find the temperature after some time. For example, you can find the temperature of the object after 1 hour. 1 hour, maybe you can substitute the T with 60 minutes, and you can find out your temperature, right? You can find the temperature after 60 minutes, all right? So this is the application of first order differential equation in cooling. Alright, that's all for this video. We will go more examples in next video.